So Otfried forgot to mention that actually I met another beautiful woman in Utrecht, which is his wife. So I used to share office with her. So okay, so I will be talking about the Fibonacci dimension of a graph. This is joint work with David Eckstein and Sandy Closure. So David is from US and Sandy is in the same department as I am. So this is what, well, I mean, actually these are not options. We will have to eat everything here. So I will first talk about concepts. So this is the objective of the talk, Fibonacci dimension. But somehow it is difficult to understand what is it about if first I do not introduce some more traditional dimensions. So the most traditional dimension is isometric dimension. And then we have lattice dimension, which is rather natural, as you will see. So I will first explain these concepts. And then I will talk a little bit about combinatorics of the Fibonacci dimension and a little bit about algorithmics. So if you have any questions, please ask at any point. Okay, so one of the main objects we will look at are hypercubes as a graph. So the hypercube as a graph of dimension d is here. So what we do, or what has as the vertex set, is the set of binary strings of length d. Okay, so here we have an example of dimension 3. And two vertices are adjacent if the strings differ in exactly one position. Okay, so here we have this string and this string, they differ in the third position, so we put an edge between them. And we only put binary things, zeros and ones. So the distance between two vertices in the graph, so here there are no weights, this is an unweighted graph. The graph distance between two vertices is precisely the Hamming distance of the strings. And, well, so it is convenient to think of the 0 as the first coordinate, the 1 as the second coordinate, and the 0 as the third coordinate. So to think coordinate-wise. Okay? So I guess that everyone has seen this. Another important object for us is partial cubes. So a partial cube is an isometric subgraph of hypercube. So what you're doing is you're selecting a set of vertices, and then you look at the graph induced by those vertices. So you put the edges, you consider the edges between all those vertices, and you should have the property that the distance in the remaining graph should be equal to the distance in the original graph for any vertex that survives. Of course, the ones that get killed here, the ones that disappear, they are not relevant for the distance. Okay? So this is not actually the induced subgraph by some vertices, but for 3D this is a good picture. This is actually, this statement is not true. And well understood objects, I mean, partial cubes have been studied for quite a while. So basically, well, you can never tell that everything about them is known, but perhaps it is already. Okay? This is not a partial cube because the distance between these two guys in the original graph is 1, while in this graph it would be 3. You have to go around here.
What if I add that vertex? No, among the delete that one.
If you add this one with this edge, this would not be a partial cube because the distance originally was 2.
So I have to add more things?
Yes, you would have to add more things.
So then it's not all induced subgraph?
No, it's not induced. So it should be induced and the same distance as originally. So yes, this statement is misleading. Okay? Thanks for the questions. I will pay you a beer. Okay. Okay, so what is the isometric dimension of a graph? Is the smallest dimension such that G can be isometrically embedded into the hypercube of dimension D. That's the definition. So you're given a graph. It has no labels. It has nothing. It's an abstract graph. And now you would like to embed it isometrically into the hypercube, which means distances in the original graph should be equal to distances in the image. And you would like to use as few dimensions as possible. Okay? And that's the definition of dimension. So, of course, there are objects that have isometric dimension infinity. For example, the triangle. Why is that? Well, the hypercube is a bipartite graph. The triangle is not bipartite, so you cannot isometrically embed the triangle into any hypercube. Of course, there are 1,000 examples. Okay, so particularly we can talk about the isometric dimension being infinity or being finite. Infinite or finite. The isometric dimension is finite if and only if the graph is a partial cube by definition, or is isometric to the partial cube. And in some sense, if you're given a graph and you would like to know its isometric dimension, what you have to do is to each vertex you have to attach a binary label, and what you would like is that the distance between the labels, well, this. So the induced subgraph by these labels and G should have the same distances. So it's not just that you should attach a label and the Hamming distance between the labels should be the correct one. You also need a little bit more structure. So it should be a partial cube. I mean, so it should be isometric in the hypercube. Okay? Okay, so this has isometric dimension 3, as we saw before. Because you can, well, because you could ask whether it has dimension 2, but it cannot be because it has 5 vertices. And this is a little bit misleading because here I was telling this is not a partial cube because it is, well, but actually it is if you use one dimension more. Okay? So, well, I put a 4th dimension and then somehow this goes into one dimension and this goes into a different dimension. Okay? So now this is actually a partial cube. But it's not a partial cube coming from the 3-dimensional cube. It's a partial cube coming from the 4-dimensional cube. Okay? Any questions, Otfried? Okay. Okay. So something that a priori is not clear is the isometric dimension can be found in polynomial time. The standard way to do this is so-called via theta classes. So you can classify the edges into classes. And then, well, if they are an equivalence class, I mean, you have to look at the definition, but if they are equivalence classes and the graph is bipartite, then it is a partial cube, and the dimension is actually equal to the number of theta classes, but we will not be using this at all, so I would skip this. The important thing here is you can compute the dimension in polynomial time. Something that we will use is that there is actually only one isometric embedding of G into the cube, into the cube of minimal dimension up to the things you can do with the hypercube. So what you can do is you can reorder the string coordinates. So you could say I exchange the first coordinate and the third coordinate. So that will give you another embedding, which is also isometric. And what you can do also is switching the rows of 1 and 0 in some coordinates. So you can say in coordinate 2, I switch 0 and 1. In coordinate 6, I switch 0 and 1. And that's everything you can do. You cannot do anything else if you want to keep isometric embeddings into the cube. And then what happens is that when you put a dimension which is larger than the isometric, the only thing you can do is to put dummy coordinates. So what is a dummy coordinate? So that's a coordinate that it always has value 0 or it always has value 1 for all points. So it's a coordinate that is irrelevant. Okay? If you think geometrically what this means or what you can do is only to use symmetries of the hypercube. So there is one embedding into the hypercube which is isometric up to isometries of the hypercube. Isometries is basically, well, reflections of coordinates which corresponds to switching the rows of 1s and 0s and, well, rotations that bring one coordinate over another coordinate. Okay? So is this clear? Because I will be using this later. So there is essentially one isometric embedding. Or you can have dummy coordinates. These of dummy coordinates? Yes, so all this is sort of, well, it depends what you mean by easy. But all this, so once you understand these theta classes that are here, so once you understand these theta classes, a lot of things come for free. This definition of theta classes is completely non-intuitive, actually. So So you should be given the definition. That's not something I would come by myself. On the other hand, it appears in textbooks already, so it's not difficult. Okay, next dimension, the lattice dimension. So we do the same, but instead of embedding into the hypercube, we want to embed into a lattice. So what we do is we look at ZD with the L1 metric. And then what we want is given a graph to embed it into ZD and minimize this D and minimize the dimension. Okay? And we would like also to be an isometric embedding. Okay? So this would be a graph that has dimension 2, because of course you cannot embed this into the line, because in the line you can only embed paths. Okay? So this is the lattice dimension. So we can think of this like before. So what we want is to attach to each vertex string with integer values in each coordinate, such that the induced subgraph of ZD with the L1 metric and G have the same distances. Okay, so this is very intuitive. Something that is perhaps not so clear: the lattice dimension is finite if and only if the isometric dimension is finite. So basically, the lattice dimension is finite only for partial cubes. We'll give you the proof in a second. Well, actually I can give it. So what you do basically is from here you move to here. So how you do this is here, so you need, for the first coordinate you need values between 0 and 4. So what you will do, you will use a string of length 4, which can be, well, from 0, 0, 0 to 1, 1, 1, 1.
But if you can embed it into a cube, isn't that automatically a lattice?
Yes.
Embedding?
Yes.
Yeah. Oh, I know. The other way.
Yes. So what that shows is that if it is isometric dimension is finite, then the lattice dimension is finite, yes. Okay, so this is what you would do. So here you have 0 and 2, so you will replace this by all zeros, and this that represents 2. So here you have 3, 1, and what you do is you represent by 1, 1, 1, 0, and then 1, 0 for the second coordinate. And this is just a valid mapping from the lattice to the hypercube. Of course, you will need several more dimensions. Okay? Something that is also not trivial to see is that the lattice dimension can be determined in polynomial time. And actually, this is a quite recent paper in 2005. And it always, well, so somehow the approach that is used in this paper is similar to some things I will be describing. So somehow the fact that, so this is an isometric embedding into a hypercube now, and then somehow what you would have to do is to find out which coordinates you can pair together. So that's everything you have to do to come back to what we had before. I mean, to go from that to this. Okay, so that's the isometric dimension, the lattice dimension and the isometric. So now we will move on to Fibonacci dimension. So first, what is a Fibonacci string? So a Fibonacci string is a binary string without two consecutive ones. So standard examples. So this is a binary Fibonacci string, this is a Fibonacci string, and this is not, because we have two consecutive ones. And here we have two consecutive ones. So these are not Fibonacci strings. So the name comes from Zeckendorf's theorem, which is a little theorem from number theory. Well, little or not, but it's quite basic thing. So each natural number can be expressed as the sum, can be expressed uniquely as the sum of Fibonacci numbers without being two Fibonacci numbers consecutive. Does this make sense? Okay, when you look at the Fibonacci numbers consecutively, you never have to use two which are adjacent. And that expression is unique. The number of Fibonacci strings is equal to the number Fn, the nth Fibonacci number. So that comes from Zeckendorf's theorem, or you can just, okay, so the number of Fibonacci strings, you have two options. If the first coordinate is a 0, then you can put whatever you want here, so Fn minus 1. If the first coordinate is 1, then here you should have a 0, and then here you can put whatever you want. So you get the Fibonacci recursion. So the number of Fibonacci strings is Fn also. So what is the Fibonacci cube? So I will use gamma and d for the dimension. So it's the subgraph of the hypercube of dimension d induced by the Fibonacci strings of length d. So you only look at those Fibonacci strings. Something that you have to prove, but it is not difficult, is that gamma d, the Fibonacci cube of dimension d, is actually a partial cube. So the distances here are the same as they used to be in the original hypercube. That's quite easy to see. Sorry?
What's the distance?
The distance.
Yeah.
So this is a graph. So let me show you an example. So this is a partial cube. This is a Fibonacci cube of dimension 3. So you had the original cube of dimension 3, and now you only look at the, actually this is not because it has here. This is not an example. This is an example. Okay? So you look at the strings that are Fibonacci strings. So the one that would be here would be, well, I should think, 0, 1, 1. Yeah? So this would not be a Fibonacci string. So you cross out these people from the original graph, and you look at the remaining. Yes?
The distance is usual distance in graphs.
Yes, yes. It's the usual graph distance. I will come back. So this is the Fibonacci cube of dimension 10 according to David Eckstein. So I didn't check it. So he made this figure. He claimed that this is the Fibonacci cube of dimension 10. Okay, so let me go back. So what I was telling is the Fibonacci cube of dimension d is isometrically embedded. So the distances are the same. And actually it has a stronger property, which it is a median graph. So I guess it doesn't matter here what is a median graph. Does anyone know what is a median graph?
About from the planar graph?
No. So it doesn't matter. So median graph is a strong property that you would like that all your graphs would have, but typically they don't. So what it means is whenever you take 3 vertices in the graph, and you look at the shortest path between all pairs, right? So you look at this shortest path, you look at this shortest path, and you look at this shortest path. If the intersection of all them is precisely one vertex, and this holds for all triples, this is a median graph. So this is an extremely complicated thing, but it's extremely useful. So when your graph is median, you have a lot of properties. In particular, it is a partial cube. But so this is called the median of all 3 vertices. Okay, so Fibonacci cubes appear in chemical graph theory. So it's the resonance of certain hexagonal chains. So when you have a hexagonal chain, then you look at perfect matchings there, and then you define some properties of adjacency between different perfect matchings. And well, it appears Fibonacci cubes. It was actually proposed originally as a network topology for parallel computation. And the last remark is, given a graph, if you're interested in knowing whether this is a Fibonacci cube or not, so that can be solved in near linear time. So it's not straightforward how to do it, as we will see later, because actually we will see that some problems related to this are NP-hard. So this is actually decidable really quickly. Okay, these are the examples, and this here I wanted to mention something that will pop up later, which is this is not the Fibonacci cube because I didn't choose the appropriate labeling. Okay, so the graphs are the same. This is a Fibonacci cube because I choose the appropriate labels, but you have to be careful which labels you use, right? And this is something that will pop up later. Okay. So what is the Fibonacci dimension? So I guess that everyone can guess by now. So is the smallest integer f such that G, the graph G, can be isometrically embedded into the Fibonacci cube of dimension f. Okay, so what we have to do, to compute this dimension is basically attach Fibonacci strings to each vertex such that the induced subgraph of the Fibonacci cube and G have the same distances. That's what you would like to do. Okay, so these were the concepts so far. Now what I will talk is a little bit of relation between Fibonacci dimension and other dimensions. The Fibonacci dimension of some particular families of graphs, and a little bit of algorithms of Fibonacci dimension, and in particular why it is hard to compute.
So the question. So you say induced subgraph of gamma and G have the same distance. So
Yes.
Perhaps when you measure the distance in gamma f,
Yes?
no, I mean you want to use distance found in gamma f, not in the induced subgraph.
In the induced subgraph. Because, okay, so let me so let's say here a path of length 3, okay, well, with 3 vertices. So you could you could embed it here like this. Yeah, so perhaps you're right actually, yes. So you should be, so let me think. So you look at the vertices, and then you look at the, no, I think it's fine to look at the induced subgraph. But now I'm confused by your question. So, so whether you should look, okay, so you have your graph G, and now you are embedding this into gamma f, and now you want that the distance between, okay, so let's call this phi. So the distance between u and v and g should be equal the distance between the images. And what should I put here? Gamma f, or should I put the portion of gamma f that is induced by the image of this? That's the question.
Yeah.
So I don't know. So I'm not from this field. So.
I imagine that since you said isometric embedding,
Mm-hmm.
then
You should look here. You should look at the ambient space, probably, yes. So you should look here, probably. Which means that what I'm telling is not precise. But
The second one would be meaningless.
would be meaningless.
Yeah, because it's just same distance as the but the image itself should be induced.
The image should be isomorphic to the original graph, yes? When you look at the edges that are there, yes? So that means that an edge is in the image if and only if it was originally. So that seems to indicate that induced is fine. Yes, yes. So definitely you should measure in the Fibonacci, because that's the definition of isometric. I mean, you look at the ambient space without taking care of which proportion you are taking. Yes. So what that means again is that, okay, so this statement should be crossed out. Thank you. The remark. I should come more often to realize some more mistakes. Okay, more questions. Okay, so the first relation to other dimensions. So the isometric dimension is more or equal than the Fibonacci dimension. So why is that? Okay, so if you can embed G isometrically into the cube of dimension f, then we said that this cube is isometrically embedded into the hypercube. So therefore G can be isometrically embedded here. Okay, so this implies this relation. And now it is when the tricks start. So the Fibonacci dimension is more or equal than twice the isometric dimension minus 1. So why is that? Okay, so assume that you have an isometric embedding that sends a vertex V to this label. So this is just an example, dimension 5. Now what you can do is you can embed this into the Fibonacci dimension just by padding dummy coordinates in the middle where everything are zeros. So this is of course a Fibonacci string now. There are not two consecutive ones. You need d minus 1 extra dimensions. And now you should argue that the distance here is actually the same as it was here. But that's quite simple. Okay? So this shows this relation. This in particular implies that the Fibonacci dimension is finite if and only if the isometric dimension is finite, if and only if the lattice dimension is finite. So we only need to study these things for partial cubes. Okay. Some other relation to other dimensions. The lattice dimension is smaller or equal than, well, roughly the Fibonacci dimension divided by 2. So why is that? Okay, so you can use induction in the dimension, and we will provide an isometric embedding from the Fibonacci cube of dimension f into z. Well, this is the Cartesian product of graphs, but just I think I will not define it. But the idea is you will have from u, you will get a coordinate that is using 2 dimensions less, and then something that is from z. Okay? So this is a binary, this is a binary string, this u star. This is just a binary string because you are here, and this can be integers. Okay? And then you measure here the L1 distance of this thing. How do you do this? Okay, so you look at the first, you want to delete 2 coordinates. Okay? So if you had a 0, 1, you put here a 0. If you have a 0, 0, you put a 1. If you have a 1, 0, you put a 2. 1, 1 cannot be, because this is coming from a Fibonacci string. Now, the distance between this, a point that looks like this and a point that looks like this, so it is 1 plus the distance of the remaining. Okay? And here the difference will be 1 plus the distance of the remaining also. So this is a valid isometric embedding. And now you just, well, use induction. Okay? Well, here of course the distance between 0, 1 and 1, 0 is 2. So this is what you need here at 2. This is quite intuitive, I believe. So now you just use induction, and then you get an isometric embedding from the Fibonacci cube of dimension f into, well, roughly f divided by 2. So for each 2 dimensions less, you need an extra z. And now you have a graph that isometrically embeds here, then this isometrically embeds here, and therefore you get this bound. Okay? Because this is also what you get here is an upper bound for the lattice dimension. Another relation that I will not attempt to explain, but basically the Fibonacci dimension is bounded by the isometric dimension plus the lattice dimension minus 1. So here you need a little bit more of Cartesian products and so on. It's really simple, but just I have to skip some things. What is important here, this is better than what we proved here before. So here we have isometric dimension plus isometric dimension minus 1. And now here we are moving to isometric dimension plus lattice dimension minus 1. So this is stronger. Okay. Some Fibonacci dimensions for some families. A tree. So the Fibonacci dimension of the tree is equal to the number of edges of the tree. Actually, it is known that this is also the isometric dimension. So the isometric dimension of the tree is equal to the number of edges. So basically, for each edge, you need an extra dimension, because otherwise things would not be isometric. So since it is known that the isometric dimension is equal to this, and the Fibonacci dimension has to be bigger, we only need to provide an embedding into the Fibonacci cube of dimension this much. That's everything we have to do. And this is the embedding. So proof by example. So you take your tree and you take the diameter of the tree. So this the diameter. Okay, and you pull it there. And now you choose as root the central vertex, which of course might be a little bit unbalanced, which is what happens here, but basically this is the distance from here to here is the same than to here plus perhaps 1. And now you hang the tree from the root. Now you order the edges as follows. So you start with this one, and then this is the first, the second, the third, the fourth. 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, and so on. Okay? And now to a vertex, like for example V, you attach the characteristic vector of which edges you need to visit when you go from the root to that vertex. So here basically you will have zeros everywhere, but in the first coordinate, the 5th, the 12th, and the 19th. So this is what you get here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So this is the embedding. So here, of course, the number of coordinates is equal to the number of edges. So why is this a Fibonacci string? Also, you have to argue that you never have two consecutive ones. So why does this happen? Well, because the way how we order the edges. So if you have a 1, I mean this is a 2 and there is no vertex that would be using both edges. Okay, so in this ordering there is no vertex that uses two consecutive edges according to the ordering. Okay. Here we are using that, well, I mean if here this would keep going down, then you would have a problem if this would be here the 20, the 21, and the 22. So this is the reason why I had to break it into two pieces of the same size. That whenever you have an edge here, you will have one in the other side. So that you are alternating from side to side always. Why is this an isometric embedding? Well, so if you want to go from V, let's say, to this vertex, so you have a part that is in common, and then you have these edges, which is the symmetric difference of the set of what you're visiting. So it's very much straightforward. So this is a proof by example. In the paper, actually, we develop a machinery that allows you to prove which one is the Fibonacci dimension. So if you try to read the paper, this is the proof that is completely different to this, actually. I believe that this is more understandable, and this is actually how we thought. But then, of course, if you prove 1,000 theorems before, then there is a more compact way to write down things. Okay. Another thing has to do with the Cartesian product, which I decided, well, I will just skip it, because otherwise I have to explain what are Cartesian products. And there are other things that I think will be more interesting. Okay. So now actually I will come to the main characterization that we found, and this is what we use as machinery everywhere. So which is a characterization. So when can I tell that a graph has such Fibonacci dimension? Okay, so as we were mentioning, we only have to look at partial cubes. So let G be a partial cube of dimension D. Then what we are doing, I mean, so we can attach, I mean, because it can be embedded into hypercube of dimension D, this means that you can attach binary labels of length D to each vertex, and then the distance between the labels are the same as in the hypercube, as in the original graph. Okay. Now, what does it mean, the Fibonacci dimension? Okay, so what we were telling that you can do for free, and actually, well, we had these symmetries of the hypercube. So we were telling that what you can do is reordering the string coordinates and switching the rows of 1 and 0. Okay, so these are things that you can do. And now basically what you are going to do is to insert the minimum number of dummy coordinates that will be always equal to 0, such that you can reorder, you can switch, and all the labels that arise are Fibonacci strings. Okay? So this is basically the rules of the game. I mean, you can think of this like a game. So I give you a graph that is embedded isometrically in the hypercube of dimension D. So each vertex has a label. Okay? And now what I want is, well, I want to insert the minimum possible number of extra coordinates that will be always 0, because zeros are better than 1s for Fibonacci strings. I mean, they are not symmetric. And now you want to switch to reorder some coordinates, to exchange the role of 0 and 1 in some coordinates, and that everything will be Fibonacci strings. Okay? So those are the rule of the games. And what you want is to minimize the number of dummy coordinates. Now, you can formalize this using an associated graph, which we denote by xg, basically, I guess, because we didn't have better name. So this is what you do. So you started with, this is an embedding of this graph into the hypercube of dimension 4. Okay? And now a good way to look at this is you make groups. So this is the set of vertices that in the first coordinate have value 0. And this is the complement. So the set of vertices that in the first coordinate have value 1. Okay, so this is, you should think of this like a pair. Here you have another pair, the set of vertices that in coordinate 2 have value 0, and the set of vertices in coordinate 2 have value 1. If you find some mistake, let me know, because I'm planning to reuse this slide. So, okay, so this is thing. This is what you have. Okay, now, what does it mean reordering? Okay, so reordering means that you should tell, okay, so this was my first coordinate, this was the second, this was the third. Okay, so somehow you have to find an ordering of these people. So reordering means like you could tell now this is the first, this is the second, this is the third coordinate, and this is the fourth coordinate. So this is what you can do. So you somehow need some ordering among these people. And what does it mean to switch ones and zeros in a coordinate? So what it means is that, well, so here the first coordinate was taking value 1, but now basically you could exchange all these people. So here wherever you had a 0 and a 0, you could put here 1, 1, 1, 1, and here 0 and 0. And that would be like a legal move. Okay? So what does it mean, this reordering coordinates and switching zeros and ones? It means that you want like a path that will visit group after group, and in each group you should choose which one will get the role of 1 and which one will get the role of 0. So you should tell, so I want that these vertices, they get in the, in the coordinate value 1, or these vertices get in the coordinate value 1. You have to choose which one of the two. Okay? And now what you want is that the resulting things are Fibonacci strings. So what does it mean, Fibonacci string? Well, so let's say here you have 0, 1, 0, 1. This 0, 1, 0, 1 is also here. Okay? So to tell that these vertices should get in coordinate I value 1, then I cannot tell that these vertices should get in coordinate I plus 1 value 1. Okay? Because otherwise I could not get a Fibonacci string. Okay, so then I put an edge whenever the sequence is allowed. So I can tell that these people get value 1 in a coordinate, and this, the next one, to be value 1 in the coordinate. And why can I do this? Okay, because they are disjoint, these sets. So if the set of vertices here is disjoint from the set of vertices here, then I add an edge. Okay? So this is the graph xj. And now here what you have to do is like this path. And now this resembles a lot like Hamiltonian path, if you want to don't add extra dimensions. But sometimes, you know, so this graph could be the empty graph. In which case it means that you will have to put a lot of zeros, because there is no way to put two things consecutively. So if you look here, so here I got a path, so you have W11, so you start here. So I will tell, okay, so these people will be, we have the first coordinate equal 1. Then I move to 3, 1, which is here. So these people will have the second coordinate equal 1. Then I move to 4, 1, so here. These people will have in the third coordinate value 1. And W2, 0, so I move here. These people will have in the fourth coordinate value 1. Okay? and somehow like this sort of pseudo-Hamiltonian path gives me an embedding. Okay. So actually, well, that's it. So basically here, W11, so it means the first coordinate, it is actually the first one as it used to be. The second coordinate, it is the one that used to be the third. The third coordinate now is the one that used to be the fourth. And the fourth coordinate is the one that used to be the second, but now I should switch the rows of zeros and ones. Okay, and this is the transformation that you get. Another example. So if you start with this partial cube, so you can make the construction, and now you have here the problem of, okay, so after putting to these people value 1 in one coordinate, I can tell that the next coordinate is this one with value 1, but now I have no other choice. So now I have to put an extra coordinate, a dummy coordinate that is always 0. Okay? So this is what you get. W11, W31. Now I will put a dummy 0, which is just to ensure that everything are Fibonacci strings. And then you put the next one, the 2-1. So actually, to embed this in a Fibonacci cube, you need an extra dimension. Okay? And here, everything I said is basically if and only if. So if you could get an embedding, I mean, such labels with Fibonacci strings, it means that here you can find a set of these paths, which, well, you have this property. So you want a set of paths that visit from each pair exactly one vertex, I mean, one of the nodes, and visits each pair, and you want to minimize the number of these paths. Okay, so that is basically the characterization. So given a graph, you embed it into, I mean, as a partial cube, and then you look at this associated graph, and then you are searching for some paths there. Okay, bad news. It is NP complete to decide if the isometric dimension is equal to the Fibonacci dimension. So I will give you a proof also, but the idea is the following. So as I was telling, that problem resembles a lot to Hamiltonian path, and actually you can reduce from Hamiltonian path if you use the appropriate graph. So for a given input graph H, you construct the two-simplex graph, which I will describe what is now. And now it holds that the isometric dimension of this two-simplex graph is equal to the Fibonacci dimension if and only if the original graph had a Hamiltonian path. That shows NP hardness. So this is the proof. So you start with this original graph, and you look at the complement. So this is the complement graph. And now for the complement, you look at the two-simplex graph. So what is this? So here you have, okay, a vertex from the empty set, a vertex for each vertex you had here, and a vertex for each edge. So here you have the edge 3, 4. So then you put here a vertex corresponding to that edge 3, 4. And now you add the edges by inclusion. Okay, whenever you have an inclusion of this, you put an edge. So this is a standard construction. This is a partial cube, and it holds that the dimension of this, I mean the isometric dimension here is equal to the number of vertices you have here. So the isometric dimension of this graph is equal to 6. And now you look at the associated graph we were telling before, xg, and what you get is this xg. So what is this? Well, so you have some, so we had these pairs before, right? So I was having these pairs of things. Okay, so here you have pairs, but one of them never has any edge. So you can forget about them. And the ones, what you get is actually the original graph. Okay? Now here what we were telling is you want to find here a path that visits this, well, so from this group it should visit one of them, but it cannot visit this one because it doesn't have any edge. So here you are looking for a Hamiltonian path. If here you have a Hamiltonian path, it means that you don't need to add any extra dimension. So, well, basically the Fibonacci dimension is equal to the isometric dimension if and only if here you have a Hamiltonian path, which is if and only if here you have a Hamiltonian path. the reduction is extremely easy once you realize, well, that you should look at the two simplex graph. Okay. More algorithmic results. So as we saw, this problem is closely related to Hamiltonian path. And actually, it is a Hamiltonian path with weights 1 or 2. So an edge is there, weight 1, and edge is not there, weight 2. So Hamiltonian path with weights 1 and 2 is a well-studied problem. So you should go to the bibliography, know what is the best you can do there, and see what of those things you can apply here. So that's what we did. So basically, it turns out it is NP hard to approximate the Fibonacci dimension within this number, which no one expects to be the correct one, but essentially you cannot get arbitrarily closed. Something that we could show is that it is approximable within 3 halves, and the idea is quite simple. So when you look at this graph here, you look at maximum matching here. A maximum matching here corresponds pair of coordinates that you can put together, because they will never have pairs of 1. So you just compute a maximum matching in this graph, and then you play a little bit with the numbers, and that gives you 3 halves. So this also resembles a lot to the 3 halves approximation to to TSP, right? So there you also compute a matching, and then you relate it with the optimum and so on. Just here things are unweighted, so things are easier. It is possible also to compute the Fibonacci dimension exactly in exponential time in k, where k is the isometric dimension. So now, well, this is a little bit cheating, because if you have n vertices, you need that k is at least log n. If you want n vertices in the hypercube, you need at least log base 2n dimensions, because otherwise there is not enough space. So that means that, well, here you could put, I don't know, if you want that this is polynomial, you shouldn't put here something bigger than log. But we were using this as a subroutine to get a 1 plus epsilon approximation for simplex graphs. So before I said what is a 2 simplex graph, so what is a general simplex graph, so you do the same, but you do not stop in the edges. You then look at the triangles, at the clique of size 4, cliques of size 5, and so on. Now here there is also a little bit of cheating, because this graph, if it has n vertices, the corresponding simplex graph can have huge size. Okay, so basically it can have size 2 to the n. Basically, this is the complete graph. Here you will have, well, here you have all cliques, which means all subsets, which means this has size 2 to the n, basically. So here we take as input the simplex graph. So that's how you get a 1 plus epsilon approximation. And now something that is quite general and, well, I like a lot. So here what we use is actually something that could be seen as approximating pairs of pairs. And David Eckstein worked further on this. So what is this? So assume you are given a graph. So if you want to find a maximum independent set, that is an extremely hard problem. So actually you cannot approximate it within basically nothing. If you want to find a longest path, a path as long as possible, so that is really bad also you can do. So you can approximate it also within n divided by log n. Basically, well, polylog I think is currently, but even for graphs that have Hamiltonian paths, they do not know how to find bigger than polylog, I think. But now what you can look is at the pair of problems. So given a graph, can you find a large independent set or a long path? And with either of them, I will be happy. Okay, so this is a problem about, so given one input, you look at 2 problems, and you would like to be able to tell something good in one of them. So this is actually what we look here, and this is what we use here inside. But actually there is a follow-up paper by David Eckstein that basically works only on this. So approximating or inapproximability of pairs of problems. Which, well, so it's just a new paper, so it might be interesting to look in some problems for this. And that's basically everything I wanted to tell you. Thank you.
Any questions?